Hello students, this is my sixth lecture with you on PDE, and today we shall see homogeneous and non-homogeneous linear PDE with constant coefficients, and especially today's class will be on method of solution of homogeneous linear PDE. So what is homogeneous linear PDE and non-homogeneous linear PDE with constant coefficients? A homogeneous linear PDE of nth order with constant coefficients in two independent variables x and y and one dependent variable z is a PDE of the form of this form. What is the form? Del nz by del xn, that is nth derivative of z with respect to x, partial derivative, plus k1 into del nz by del x n minus 1 del y, that is nth derivative of z with respect to x n minus 1 times and with respect to y 1 time, plus k2 into del nz by del x n minus 2 del y square. Nth derivative of z, it is mixed nth derivative of z n minus 2 times with respect to x and 2 times with respect to y, plus dot 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 kn minus 1 del nz by del x del y n minus 1 and plus kn del nz by del y n, that is nth derivative of z with respect to y, or nth partial derivative of z with respect to y plus term is equal to f of xy, number 1, where k1 k2 kn are constants in which all the partial derivatives occurring are of the same order n. See, in every term the order of partial derivative is nth order, maybe mixture, but order is n. And right side f of xy is a function of x and y, denoting del by del x, that is partial derivative with respect to x operator by capital D, and del by del y, that is partial derivative with respect to y, that operator by d dash, capital D dash. In PDE, this is the usual practice. The PDE number 1 can be written as d to the power n k1 d to the power n minus 1 d dash plus k2 d to the power n minus 2 d dash square plus dot 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 kn minus 1 d into d dash to the power n minus 1 plus kn d dash to the power n operating on z equal to f of xy, or f of capital F of d comma d dash is equal to small f of xy, number 2. Both are the same. Where capital F of d comma d dash is equal to d to the power n plus k1 d to the power n minus 1 d dash plus dot 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 kn d dash to the power n is a polynomial expression in d and d dash in which every term is of same degree, that is f of d comma d dash is a homogeneous expression. If f of d comma d dash is equal to small f of xy, number 3, is a PDE where f of d comma d dash is a polynomial expression in d and d dash, but each term in it is not of same degree in d and d dash, that is f of d comma d dash is not a homogeneous expression in d and d dash, then the PDE number 3 is called a non-homogeneous linear PDE with constant coefficients. For homogeneous, order of derivative in every term is same, here it is n, and for non-homogeneous it may be different, that is if we use this notation, then degree of every term is n here, and for non-homogeneous this f of d dash is not like that. In different terms there may be different degrees. Okay, example will clarify it. For example, del square z by del x square plus 3 del square z by del x del y plus 2 del square z by del y square equal to x plus y is a homogeneous linear PDE with constant coefficients. Coefficients are constant and order of derivative in every term is second order, so it is homogeneous. Number 2, del cube z by del x cube minus 3 into del square z by del x square plus 3 into del square z by del x del y equal to del z by del y is minus del z by del y, minus del z by del y equal to x minus y is a, this PDE is a non-homogeneous linear PDE with constant coefficients, because see, first term is third order derivative, second term is second order, third term is again second order mixed, fourth term is first order partial derivative. So different terms are of different orders. That's why it is not homogeneous. It is non-homogeneous. Now, solution of linear PD f of d comma d dash equal to fxy, general form, with constant coefficients, of course. Similar to the case of linear ordinary differential equation we have done in first semester with constant coefficients, the general solution to the PDE 1 consists of two parts, complementary function CF and particular integral PI. The CF of the PDE number 1 is the most general solution of the PDE f of d comma d dash operating on z equal to 0. Means when number 1 right side you consider 0 and solve this PDE, corresponding PDE, then the solution of that PDE, general solution of that PDE is called CF, complementary function. And any particular solution of number 1, PDE number 1 with fxy, right side, is the particular integral. The general solution of this PDE number 1 is given by z equal to CF plus PI. Now method of finding CF. How to find CF? How to find PI? First we shall see CF. Let us consider the second order linear homogeneous PDE with constant coefficients, del square z by del x square plus k del square z by del x del y. It is k1. K1 del square z by del x del y plus k2 del square z by del y square equal to fxy, number 1. First we consider the PDE, same PDE, but right side is 0. F of xy removed. Del square z by del x square plus k1 del square z by del x del y plus k2 del square z by del y square equal to 0, number 2. And the solution of this number 2, general solution of this number 2 is actually the CF of the PDE number 1. So this equation can be written as d square plus k1 dd dash plus k2 d dash square operating on z equal to 0. And suppose this expression when factorized we get this d minus m1 d dash into d minus m2 d dash operating on z equal to 0, number 3. Where m1 and m2 are suitable constants, clearly solution of any one of d minus d1 m1 d dash operating on z equal to 0 or d minus d2 d minus m2 d dash operating on z equal to 0 with two factors, 2 PD. Solution of any one of them is also a solution of number 3, because if we consider the equation d minus m1 d dash z equal to 0, then solution of this which will make this equation the value of z which will make this 0, automatically this operates on first. Okay, here this can be interchanged. This d minus m2 d dash can be taken first, d minus m1 d dash can be taken second, no matter. So solution of this operating on z equal to 0 will make the LHS 0 for number 3 also. So therefore solution of any one of these two equations is also a solution of number 3. First we consider d minus m1 d dash z equal to 0, that is del z by del x minus m1 del z by del y equal to 0, that is p minus m1 q equal to r, where capital R is 0. Here it is a Lagrange's linear PD. The subsidiary equations are dx by capital P equal to dy by capital Q equal to dz by r. Here r is 0, but p means coefficient of small p, capital P here is 1, and capital Q means coefficient of small q, this is minus m1. So it is dx by 1 equal to dy by minus m1 equal to dz by 0. Therefore, considering first two, if we cross multiply, then we shall get dy equal to minus m1 dx, that is side changing m1 dx plus dy equal to 0, and obviously dz equal to 0, because here you can consider crossing this r here, dz will be r by q dy, r is 0, so dz is 0, so dz 0, and integrating this to we get m1x plus y equal to c1, and integration dz will be z equal to c2. So as if this is u equal to c1 and this is v equal to c2. In Lagrange's method we have seen, then the general solution can be written as v equal to phi of u or phi of u be 0, like that. Therefore general solution of number 4 means this number 4 Lagrange's equation linear PD is given by z equal to phi 1 of y plus m1x. This is b, this is u. So v equal to phi 1 of u means we have written z equal to phi 1 of y plus m1x, where phi 1 is an arbitrary function. Similarly, general solution of d minus m2 d dash operating on z equal to 0, that is del z del x minus m2 del z by del y equal to 0, that is p minus m2 q equal to r, where r is 0, of course, is given by exactly similar, only we shall write z equal to phi 2 of y plus m2x, where phi 2 is an arbitrary function. If m1 and m2 are distinct, then the general solution of number 2 is differential equation number 2. Our aim is to solve this number 2 first. So if m1 and m2 are different, then the general solution of the PDE number 2 is z equal to phi 1 y plus m1x plus phi 2 y plus m2x. If m1 and m2 are distinct, means solution is with two arbitrary functions, and because the order of the equation PDE number 2 is second order. So z equal to phi 1 plus phi 2 is the general solution, and because it satisfies the PDE number 2 surely. Therefore, complementary function of the original PDE number 1 is phi 1 plus phi 2. It is general solution. Z equal to this is general solution of number 2, but it is CF of number 1. Now let us assume now how to find this m1 and m2. The process we are looking into it now. Let us assume z equal to phi of y plus mx is a solution of number 2. Then dz is m phi dash y plus mx. D squared z is means it is derivative with respect to x. Phi derivative phi dash, and then y plus mx derivative with respect to x is m. Then d square z means second derivative with respect to x, it will be another m will be coming, phi double dash. Okay, then d dash z derivative with respect to y coefficient is 1, so it is only phi dash y plus mx. D dash square means again phi double dash, coefficient of y is 1. But d dash z is this line, and this line if we differentiate with respect to x, it will be m will be coming and phi double dash, so m phi double dash y plus mx. Therefore number 2 becomes, putting these values of z, dz, d square z, dd dash z, etc. in number 2 we get m square plus k1 m plus k2 into phi double dash y plus mx. Every term contains phi double dash y plus mx equal to 0. Implies m square plus km plus k2 equal to 0. Since phi is an arbitrary function, phi double dash is arbitrary, so this part must be 0. This equation number 6 is called the auxiliary equation. And m1 and m2 as considered above, already we have considered, are roots of this equation number 6. If we factorize this, we shall get values of m1 and m2. This equation 6 can be obtained by, now how to obtain this equation 6? Very easily can be obtained by just replacing d by m and d dash by 1 in LHS of number 2 and equated to 0. You can see number 2. Directly you can write. If we replace d by m, it will be m square k1 m, d dash is 1, so k1 m plus k2 d dash square is 1 square m, so this m square plus k1 m plus k2 and equated to 0 will give us the auxiliary equation. It is only a way to remember the auxiliary equation, or way to find the auxiliary equation. Okay. Now if the roots of the auxiliary equation 6 are equal, that is m1 and m2 are same, suppose both are equal and equal to m, then number 3 is the equation number 3. When factorized, it is d minus m d dash into d minus m d dash z equal to 0, because originally it was d minus m1 d dash d minus m2 d dash, but m1 m2 are both m, so it is we can write d minus m d dash b equal to 0. What is b? B is d minus m d dash z. The general solution of number 7, d minus m d dash z equal to 0 is number 7, is b equal to psi of y plus mx, because already we have solved it. What we have got, solving d, you see similar equation we have solved, d minus m1 d dash z equal to 0, solving what we have got, we have got z equal to phi 1 y plus m1x. So surely here we shall get b equal to another function psi of y plus mx. Here m1 is m here. Now this implies, now put the value of b, b means d minus m d dash z, so d minus m d dash z equal to psi of y plus mx, number 8. This is del z by del x, d means del x, d dash means del y, so del z by del x minus m del z by del y psi of y plus mx equal to, or or it can be written as p minus mq equal to r, where this time r equal to psi of y plus mx, not 0. This is again a Lagrange's linear PDE of first order, and the subsidiary equations are dx by p, capital P means coefficient of small p is here 1, dy by q means here coefficient of small q is minus m, equal to dz by r means right side, here it is psi of y plus mx. From first two we get just cross side change, m dx plus dy equal to 0, integrating we get mx plus y equal to c3, or y plus mx equal to c3. Also from first and third ratio, dx equal to, we shall get dz by psi of y plus mx, but y plus mx is c3, so dx equal to dz by psi of c3, and in that crossing we get psi of c3 dx equal to dz. Now integrate, because psi c3 is constant, so psi c3x equal to z minus c4. So if we set change, instead of plus c4 we have written minus c4, you can add to the left side also, integrating constant, anything we can give. So it is z minus x psi of c3 means y plus mx equal to c4. So therefore general solution of 7 is z minus x psi of y plus mx equal to xi of y plus mx. See, our one solution of 7, we are solving 7. So one solution we have got mx plus y equal to c3, you can call it u equal to c3 like that, and here we have got z minus x psi of y plus x equal to c4, that is b equal to c4. So general solution we write function of u b equal to 0, or b is a function of u like that. So here we have written, this is suppose b, new b, so z minus x psi of y plus mx b equal to another function of u means here y plus nx, that is xi of, this is xi of y plus nx, and then side changing what we get, z equal to xi of y plus mx plus x into psi of y plus mx. So when roots are equal of the auxiliary equation, roots are, two roots are equal, then the general solution of number 2 is actually, when right side 0, z equal to xi of y plus mx plus x into psi of y plus mx, different function, only one x is here, and actually this is the CF of the original D equation number 1, CF of number 1, which is CF of original D equation we started with, that is our number 1. It is general solution of number 2, no doubt, but it is CF of the PDE number 1 considered, when right side is f of xy. Okay, so we have seen for second order homogeneous linear PDE method of solution. So in the note here we see for higher order linear PDE with constant coefficients, the method of finding CF is similar. For example, if 0, 0, m1, 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 m2, m3 are roots of auxiliary equation of a linear PDE of 7th order with constant coefficients, 1, 2, 3, 4, 5, 6, 7, 7 roots, 0 appearing twice, m1 appearing thrice, m2 and m3 are different, 7 roots of a 7th order homogeneous linear equation with constant coefficients, then its CF will be CF equal to phi 1 y, no m is 0, phi 1 y plus x phi 2 y, because repeated root, x phi 2 y plus phi 3 y plus m1 x plus x phi 4 y plus m1 x plus x square phi 5 y plus m1 x, because m1 is appearing 3 times. If 4 times, then x cube will be coming, 5, 6 will be coming. Plus for m2 and m3 different roots, phi 6 y plus m2x plus phi 7 y plus m3x. So this is the rule for finding CF of higher order homogeneous linear PDE with constant coefficients. This is just an example of for a 7th order. But in practice, you will get second order, third order only, or fourth order. Note, for a linear PDE, f of d comma d dash z equal to fxy, if d dash is a repeated factor of f of d dash, and d dash occurs r times as a factor, then the part of CF corresponding to d dash to the power r will be phi 1x plus y, phi 2x plus y square, phi 3x plus dot 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 y to the power r minus 1, phi rx. Okay, if d dash is a repeated factor of the f of d dash, that is of the operator in the PDE. So example number 1, let us see solution of this PDE. Del square z by del x square minus del square z by del x del y minus 6 del square z by del y square 0, or in symbols you can write it d square minus d dash minus 6 d dash square operating on z equal to 0. It is not into z, operating on z equal to 0. Auxiliary equation is replace d by m square, replace d dash by 1 d by m, so it will be m, and here d dash means 1, so the 1 square 1, 6 minus 6 0. So it is factorized m plus 2 into m minus 3 0. Therefore m is minus 2 and 3 distinct roots. Therefore general solution of the given PDE. Here right side is already 0. So this CF is the solution. So general solution of the PDE is z equal to phi 1 y minus 2x plus phi 2 y plus 3x. M is minus 2 and m1 is minus 2, m2 is 3. Similarly, example number 2, it is fourth order, d to the power 4 plus d dash to the power 4 minus 2 d square d dash square. Del x square del y square gives d square and d dash square, both same, operating on z. So auxiliary equation is m to the power 4, here it is 1 and here it is 1, it is m square, so minus 2 m square equal to 0. So it is m square minus 1 whole thing square 0, means m square is appearing 2 times repeated. Therefore m is plus minus 1 2 times, that is 2 pairs of repeated roots, 1 1 and minus 1 minus 1. Therefore general solution general solution means CF of the equation when right side is not 0. Here right side is 0. So this is general solution. General solution of given PDE is z equal to phi 1 y plus x phi 2 y plus x. See, 1 is repeated 2 times. Then phi 3 y minus x, m is minus 1. That is also repeated 2 times. So that's why plus x phi 4 y minus x. Number 3, homework you will do. And answer is also given. Here you will get m minus 2n minus half. That's why answer is like that, different roots. Now how to find particular integral, or what is particular integral definition also we have to give now. Particular integral, PI in short, of homogeneous linear PDE with constant coefficients. Consider the homogeneous linear PDE f of d comma d dash z equal to fxy. Now we define the inverse operator. The inverse operator f of d comma d dash is operator. It is differential operator. It differentiates partially with respect to x and with respect to y with mixture and higher order also. The inverse operator 1 by f of d comma d dash of the operator f d dash is defined by the identity f of d comma d dash operating on 1 by f of d comma d dash, and this operating on fxy finally produces only fxy. Okay, 1 by f of d comma d dash operator definition is given by this identity, means, and before that, what is 1 by f of d comma d dash fxy? By convention we define it like that, where 1 by f of d comma d dash operating on fxy gives a function or is a function of x and y. It is a function of x and y without involving, that is important, this is our assumption, without involving arbitrary constants, without involving arbitrary constants or arbitrary functions, because we want to find particular solution, particular integral. So 1 by f of d comma d dash operating on fxy is a function of x and y, again without involving arbitrary constants or arbitrary functions, and it is what? It is such a function which when operated by f of d comma d dash again gives you fxy. As if differential and integral. Differential of integral equal to function. Action of one operator neutralized by action of other. Equal and opposite force balance each other, like this in physics. So 1 by f of d comma d dash of fxy is such a function which when operated by f of d comma d dash we again get the original function fxy. And this line says that it is exactly similar to number 1, only z is replaced by what? This f of d comma d, 1 by f of d comma d dash fxy. That means what? This 1 by f of d comma d dash fxy satisfies the equation number 1, and this solution does not contain any arbitrary constant, arbitrary function. So this is a particular solution. So this is PI. So therefore z equal to 1 by f of d comma d dash fxy is a particular solution of 1, and hence it is the PI, particular integral. So PI equal to, always you shall write 1 by f of d comma d dash fxy, as if f of d comma d dash goes there and becomes 1 by, but it is not a number, it is an operator, its action is reversed. So this is PI definition, rather. Now how to find? Rules for finding PI in some particular cases. We can find PI in some particular cases, not always, not for all functions. Rule 1. When f of xy is e to the power ax plus by, pi equal to 1 by f of d comma d dash e to the power ax plus by equal to 1 by f of a comma b e to the power ax plus by, provided f of ab not 0. Just replacing d and d dash by a and b respectively, we get the pi, provided f of ab not 0. We shall see the proof later. Rule number 2, when f of xy is sine of mx plus ny or cos of mx plus ny, and f of d comma d dash here of course should be like that, phi of d square comma d dash comma d dash square means a function of even second power. D square is second power, d dash is also second degree term, this is second degree term, d dash square is second degree term. Sorry. In that case, pi equal to 1 by phi of d dash square comma d dash comma d dash square. First one is d square, phi of d square comma d dash square operating on sine of mx plus ny gives 1 by phi of minus m square comma minus mn comma minus n square sine of mx plus ny. Means, provided of course this expression not equal to 0. What is that? As if we have replaced d square by minus m square, d dash square by minus n square, and d dash by minus mn. Note that we are not replacing d by m and d dash by n, not like that. D by minus m, d dash by minus n, not like that. D dash square replaced by minus m square. D dash square replaced by minus m square, and d square replaced by minus m square. D dash by minus mn. So this is to be remembered. How? Why? We shall see later. Provided phi value of this is not 0. If it is 0, what happens? We shall see. But if phi of f of d comma d dash is not like that, means there are odd degree terms. So it is third order homogeneous linear, then d cube, d square, d dash cube will be coming. In that case, what will to be done? We shall see later. Rule 3. When fxy equal to x to the power m, y to the power n, then pi is 1 by f of d comma d dash operating on x to the power m into y to the power n is actually f of d comma d dash inverse, whole thing inverse, x to the power m, y to the power n. And to evaluate it, we expand this f of d comma d dash whole inverse in ascending powers of d or d dash, generally using by binomial theorem, and then operate on x to the power m, y to the power n term by term. There will be terms with 1 by d, 1 by d square, 1 by d cube, 1 by d dash cube, like that, and we shall term by term we shall operate on them. Means again and again we shall integrate and get the values. Okay. Rule 4. When f of xy is e to the power ax plus by into capital V, where V is a function of small x and y, then pi is 1 by f of d comma d dash e to the power ax plus by into V is equal to what? E to the power ax plus by comes to the left, and 1 by f of d plus a comma d dash plus b operates on V. E to the power x plus by comes to the left, and d becomes d plus a, d dash becomes d plus b, and it's 1 by that operates on V. This is the rule number 4. We shall see it how, why. Rule 5. When fxy is any function of x and y, any function, pi is 1 by f of d comma d dash operates on fxy, and to evaluate we resolve 1 by f of d comma d dash into partial fractions, provided it should be resolvable, considering f of d comma d dash as a function of d alone, and then d dash will be there, no doubt, but factorizing etc using the rules for partial fraction, assuming it is a function of d alone, and then operate each partial fraction on fxy, noting that 1 by d minus m d dash, this is a partial fraction. Suppose 1 by d minus m d dash operates on f of xy gives integration f of x comma c minus mx with respect to x, y is c minus mx, where c is c is to be replaced by m y plus mx after integration. After integration, because fxy you cannot integrate, when y is c minus mx, it is a function of x alone, we can integrate. So we shall integrate, and finally we shall again put y equal to c equal to y plus mx. But why? How? Let us see its proof first. Justification of rule 5. Consider the PDE d minus m d dash z equal to fxy. See, here it is pi. If this is the PDE, then pi will be 1 by d minus m d dash fxy. So this value we have calculated. That means we have to find the pi of this equation. So this PDE is considered, where d means del del x, d dash means del del y, we know. So it is p minus mq equal to fxy, which is a Lagrange's linear PDE of first order. Therefore, subsidiary equations gives dx by 1, dy by minus m, dz by fxy. First two gives m dx plus n dy 0, just cross side change and integrate, we get mx plus y equal to c. Y plus mx is c. That's why y is c minus mx. We shall see, use it later. Now, from first and third ratio dx by 1 equal to dz by fxy. So fxy, here y replace by c minus mx from this line number 3. Replace. Okay. So dz equal to fxy means f of x comma c minus mx dx, and integrate, we get z equal to integration this. So z equal to this. That means from 1, again what we see, from 1 we get z equal to means it is 1 by d minus m d dash of fxy means pi. So from 1, z equal to 1 by d minus m d dash fxy is equal to integration of f of x comma c minus mx dx, number 4. Where the constant c is to be replaced by y plus mx after integration, as the particular integral, we are finding particular integral, is not to contain any arbitrary constant or arbitrary function. So the result is true. Now, if the PDE is f of d comma d dash z equal to fxy, where f of d dash is factorizable like this, and d minus m1 d dash, d minus m2 d dash, dot, 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 d minus mn d dash, then pi is 1 by f of d comma d dash fxy, means 1 by d minus m1 d dash into 1 by d minus m2 d dash, dot, 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 1 by d minus mn d dash operates on fxy. Now first we shall find this, and then it will be a function of x and y. Then we shall find second one, this way we shall finally find 1 by d minus m1 d dash, a function of fx. So it will be coming new function, and this can be evaluated by repeated application of number 4 again and again. So this is the process for rule 5 for any function. Now, justification of rule 1. Justification may not be asked in the exam. Still, for satisfaction, let us see. We have d of e to the power ax plus by, derivative of, partial derivative with respect to x, is a e to the power ax plus by, because ax derivative is a with respect to x, y is constant when we differentiate with respect to x. D dash means del y of e to the power ax plus by. So it is derivative with respect to y, means b will be coming here. E to the power anything is that thing derivative. Now d square means second derivative of this first line. It will be del x of a to the power ax plus b, means another a will be coming. E to the power ax plus by will remain same. So a square. Similarly, d dash square e to the power ax plus by will be b square e to the power ax plus by. Then d dash e to the power ax plus by will be del x of d dash value, that is b into e to the power ax plus by. That will give us again another a e to the power ax plus by, and a will be coming with respect to x. So ab e to the power ax plus by. In general, if I differentiate r times d to the power r e to the power x plus by will give us a to the power r e to the power x plus by. D dash to the power r will give us b to the power r e to the power x plus by. D dash d to the power r d dash to the power s e to the power x plus by will give us a to the power r b to the power s e to the power x plus by. Therefore, f of d comma d dash, whatever may be the expression, e to the power ax plus by, when it operates on e to the power ax plus by, we shall get f of ab into e to the power ax plus by. Therefore, e to the power ax plus by is 1 by f of ab. F of d comma d dash operates on e to the power ax plus by. But f of ab, provided f of ab not 0, of course, f of ab is constant, so you can take inside, and therefore pi is 1 by f of d comma d dash. This f of d comma d dash, when operates on 1 e to the power ax plus by with reverse, that is 1 by f of d comma d dash e to the power x plus by. Then here also then it will become only the inside thing, 1 by f of ab e to the power x plus by, and no plus c, no plus arbitrary constant, because we are finding particular integral. So this is the rule, justified, provided f of ab not 0. When f of ab 0, let us see. If f of ab 0, then pi is, this is the pi, and 1x to the left side, and derivative of denominator f of d comma d dash differentiated f dash d comma d dash operates on e to the power x plus by, and then replace d by a and d dash by b, as if d replaced by a and d dash replaced by b. So provided f dash ab not 0. Now it may happen that f dash ab 0. In that case, again another x you give to the left side, and then again differentiate this f dash of d comma d dash will be f double dash d comma d dash, and then put replace d by a and d dash by b, get the answer. provided f double dash a b not equal to 0. The process continues via capital F dash d comma d dash, capital F double dash d comma d dash dot 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 etc. derivatives of f of d comma d dash with respect to d once, twice dot dot dot, assuming d dash constant, as if partial derivative of f of d comma d dash with respect to d, partial derivative of this. Now this rule also have proof, but we are not proving. Okay, you remember when f of a b becomes 0. Justification of rule 2, sin mx plus ny like that, or cos. So in rule 2 we assume f of d comma d dash phi of d square comma d dash comma d dash square, even second order term, every term is of second degree. Okay, we have d sin of mx plus ny is derivative of sine with respect to x, cos mx plus ny into m, coefficient of x is m. Then d square means second derivative. Again, if we differentiate, cos will become minus sine, another m will be coming, so minus m square. D dash sine will be derivative with respect to y, it will be cos, sine will become cos, and coefficient of y is n, so n will be coming here. Then d dash, if we differentiate this line with respect to with respect to x, then it will be cos will become minus sine, and another m will be coming, so it is minus mn sine of mx plus ny. D dash square means this line d dash sin mx plus ny, if we differentiate again with respect to y, this cos will become minus sine, and another n will be coming with respect to y, so minus n square, etc. Therefore phi of d square d dash comma d dash square sin of mx plus ny will be phi of minus m square comma minus mn comma minus n square into sin of mx plus ny, as if d square is replaced by minus m square, d dash square is replaced by minus n square, d dash replaced by minus mn, as if looks like that. Therefore pi is 1 by phi of d square d dash comma d dash square operating on sin of mx plus ny is this value, just reversing, taking these to the left side, etc. we get. So this is the value provided, of course phi value, this phi value is not equal to 0, and every term of phi of d square comma d dash comma d dash square is of even degree in d and d dash. But if not of even degree, then also can be applied, we shall see in the note. Now if phi of minus m square comma minus mn minus n square equal to 0, then what happens? As before in the previous note, pi will be give one x to the left side and differentiate this phi function with respect to d, phi dash d square d dash comma d dash square sin of mx plus ny, where phi dash denotes derivative of phi with respect to d assuming d dash constant, that is partial derivative of phi with respect to d, and then replace d square by minus m square, d dash by minus mn, d dash square by minus n square, provided this phi dash value not equal to 0. And if phi dash value is 0, then again give one x to the left side, again differentiate phi double dash, and then replace as usual, and the process continues. This also has proof, but we are not proving. Now in the note, in rule 2, if every term of f of d comma d dash is not of even degree in d and d dash, then also it can be applied, but keeping as it is, the factors d or d dash appearing alone, means suppose d cube is there, so d square into d square you will replace by minus m square, but d will remain. Suppose it is d dash to the power 5, then d square you will write, so d square will be replaced by minus m square, but one d dash will remain, so appearing alone after replacing d dash square by minus n square etc., and d dash by minus mn. One term may be d dash only, so it will be minus mn. It may be d dash whole thing cube also, so similarly we shall replace, and then converting them to second degree terms by operating with suitable operator, means d will remain or d dash will remain, or d and d dash separately will remain, but operating with some suitable operator, we shall convert them to the denominator of the right side while finding pi to second degree terms, and then we shall apply minus m, replace d square by minus m square, d square by minus m square, and some d or d dash will be in the numerator, and then we shall differentiate, we shall get the answer. In the example it will be explained in the next class. Justification of rule 4, we have d of e to the power ax plus by into b is derivative of with respect to x, so u into b rule, product rule, e to the power x plus by remains d of b plus b remains e to the power x plus by, derivative with respect to x is a into e to the power x plus by. So e to the power x plus bi common, db plus b means db plus ab means we have written d plus a of b. Okay, then d square means again differentiate this line with respect to x, means d of this. So d of this will be e to the power x plus bi remains d of that, this d square plus a constant so taken first, operates on b, plus d plus ab remains, d plus ab remains, then only d of e to the power ax plus b, this is a into e to the power ax plus b because with respect to x. Now e to the power x plus b common, d square plus ad operates on b, and here d plus a operates on b, so you can, and there is a also, so ad plus s square, ad plus s square, so it will be ad plus s square, and here d square plus ad, and that b taken here, you cannot take to the left side, because this is an operator, it operates on v, so it is d plus a whole thing square. So see, d square e to the power x plus b by b, but here it is d plus a whole square, as if d is replaced by d plus a, but e to the power x plus by to the left. Similarly, d dash of e to the power x plus by into b is e to the power x plus by into d dash plus b into b, operates on b, d dash plus b operates on b, and d dash square e to the power x plus by into b is equal to e to the power x plus by into d dash plus b whole square, operates on b. D dash e to the power x plus by b is equal to d of, and d dash of that we have already found, this line d dash of e to the power x plus by below, substituted here. So d of this, again derivative of this, again e to the power x plus by remains, d goes inside, d dash plus bd, b constant taken first, operates on b, plus derivative of this with respect to d will be a e to the power ax plus by, and d dash plus b operates on b will remain. So finally e to the power ax plus by taken to the left because it is into, no not operating anything on this, and d dash plus bd, and here a into d dash and ab, this operator operates on b, but this is d plus a into d dash plus b, operates on b, and so on. Higher degree terms can be simplified like that. Every time we shall see that d replaced by d plus a, d dash replaced by d dash plus b, like that, and e to the power x plus by comes to the left. Therefore f of d comma d dash when operates on e to the power x plus by into b, we get e to the power x plus by capital F of d plus a comma d dash plus b operates on b, number one. But this line is true for any function b of x and y, any function b of x and y. So we can replace this b by 1 by f of d plus a comma d dash plus b of b, because this is an operator, when it operates on b, this is also a function of x and y. So we can replace b here by 1 by capital F of d plus a comma d dash plus b operating on b. This b replaced by this, in 1 we get what we get, see, b replaced by 1 by f of d plus a comma d dash plus b operating on b in the left side of number 1. Right side is f of d plus a comma d dash plus b, and b is 1 by f d plus a comma d dash plus bb. Okay, now this f of d plus a comma d dash plus b, when operating on this, neutralize the effect. This 1 by f of d plus a comma d dash plus b action is neutralized by this f of d plus a comma d dash plus b, so it will become only b. So it is e to the power ax plus b into b, and left side as it is. Now as if this f of d comma d dash of this function is equal to that, so the pi is this f of d comma d dash comes here, suppose it is 1 by f of d comma d dash operating on e to the power ax plus by of b. See, 1 by f of d comma d dash operating on e to the power ax plus by into b, and answer is this one. This will be the answer. So it is e to the power ax plus by 1 by f of d plus a comma d dash plus b operating on. So the result is proved. Okay, and when in rule 1 f of ab 0, then pi can be obtained using this rule 4. E to the power ax plus by taken to the left, and 1 by f of d becomes d plus a, d dash becomes d plus b, and operates on what? Operates on only one. Only one. By using binomial theorem, etc. expanding, we can find one is a function of x and y. You can take constant function. So these are the results, process, methods for solving homogeneous linear PDE, and in the next class we shall see examples. Please revise the theory whatever done. The proofs of these rules may not be asked in the exam, but see for satisfaction. Thank you all.